Okay, in this video lesson, we are going to look at one of the final gas laws. We're just looking at two quantities, Gay-Lussac's law. Okay, so in class, we did a little collapsing can demo. I heated up a can. It had a little bit of water in it so that I filled the container with water vapor. Okay. So the gas was at a higher temperature here, obviously, but it was at atmospheric pressure because I had an open hole at the top in an empty soda can. Then what I did is quickly turned it upside down, dunked it in cold water, and the can collapsed. Okay, and it squeezed. Okay, and that's because rapidly the pressure of the gas on the inside decreased, much smaller than atmospheric pressure. And remember, atmospheric pressure is decently high. It's 100 kilopascals. Okay, it exerted a force, just kind of like you're squeezing the can on the can. Okay, so that illustrated this last relationship between temperature and pressure. Now remember, all of these, it's only temperature and pressure changing. Any other conditions can't change, otherwise this law doesn't stay intact. So as the temperature increases in something, okay, the pressure will increase, because if we look at this experiment, when we decrease the temperature very rapidly, the pressure decreased rapidly. So again, there's a relationship between these two quantities that are directly related to each other. They're proportional as long as you change things to absolute temperature. Okay. Again, if you were to plot temperature in Celsius versus pressure along the vertical, you would see, would follow a line, and you could extrapolate to the horizontal axis and get absolute zero there. Okay. And again, so because it looks a lot like Charles's law, it's also going to have a formula that looks a lot like Charles's law, but this time we have pressure in the top. Okay, so let's apply this to a scenario here. So we'll just look at one here, Gay-Lussac's law. Okay, what we're going to do is put all these three gas laws together, and the only thing that's missing is volume. Volume should be in the top, above temperature, and it should be multiplied by pressure. So one last law we'll look at there next is the combined gas law, where we have them all, because it's kind of hard that just two quantities change. Sometimes there's changes in a few of the quantities. So as long as we connect all those and look for those changes, we can predict one of the missing quantities in a new set of conditions. Okay, but here we'll focus on Gay-Lussac's law. We'll just look at one problem. Okay, so Gay-Lussac's, again, we're going to have initial and final conditions. P1 over T1, P2 over T2. Okay, so identifying these is crucial. So at temperature of 10 Celsius, a container is filled with a gas at a pressure of 225 kilopascals. Okay, so that looks like it's the initial stuff. It starts off at 10. What will the pressure be? Looks like the question. If the container is placed in the hot sun to reach a final temperature of 25 Celsius. Okay, so same kind of scenario as Charles's law there before. We gotta calculate the Kelvin temperature. So 283 Kelvin. This one's 298 Kelvin. Plugging it into the formula. Now, up to you. You can put the numbers in right away, or you can rearrange the formula here. P1 T2 equals T1 P2. Wow, I could have left the P's in right spots. Doesn't really matter. I find this difficult because sometimes I'm urged to put the temperature on an initial set of conditions over here because it's on the left. That's why I usually wait. I'll put the numbers in here and then rearrange, but you're kind of careful 225 kilopascals, temperature 2, 298 Kelvin, temperature 1, 283 Kelvin, and pressure 2 is what I'm looking for. The Kelvins will cancel because they're on opposite sides. I'm going to divide by 283 both sides. So this product, divide by 283. That is going to give me my pressure. So I'm going to multiply those two together and divide by 283. Sure should be 236.9 kilopascals. So does that make sense? Temperature went up, so the pressure should have gone up. Looks like it did. Not a crazy amount, but also the temperature didn't go up in a crazy amount when you're looking at it in terms of Kelvin. It only maybe went up 15 units, not quite even 10%. So we shouldn't see much of an increase in the pressure there. All right. Now these textbook references are for another textbook, so just focus on the worksheet for now for just the Gay-Lussac's law. Okay, so that's all that's there. So Gay-Lussac's law. I just want you to know these are the answers, so don't try to include those in your calculations. You'll get confused. Okay, so the last number on each line is your answer here. Okay.